These are the video notes for Objective 7, Solving Equations with Inverse Trig. Before we get into the solving equations side of this objective, we want to take a look at the inverse trigonometric functions. So in part 1 of the video notes, we're going to focus on inverse sine, inverse cosine, and inverse tangent. Let's start with inverse sine. There are two notations that you need to be familiar with for inverse sine, and that is y equals sine negative 1x or y equals arc sine x. Both of these are inverse sine. And so let's start with some definitions. The inverse sine function is a function that does the reverse of what the sine function does. So to define the inverse sine function, let's take a look at a sine curve. Okay. So a sine curve originates at 0, reaches its midpoint at pi, and terminates at 2 pi. It does the same thing in reverse. When we're trying to invert a function, we need to make sure that the function is invertible, meaning that the function is one-to-one. You may have seen functions defined or checked using the vertical line test, where you can check if the inverse is a function using a horizontal line test. Because sine is periodic and repeats the same range values indefinitely, it's not considered an invertible function. However, if we restrict the domain of the sine function from negative pi halves to pi halves, we see that no y values are repeated and that the function would technically pass a horizontal line test and therefore be invertible. So when we invert sine, we put a few restrictions on the domain and range. Specifically, the domain has to be negative 1 to 1, and the range has to be negative pi halves to positive pi halves. Now remember what an inverse function is. We know for the sine function, the input is an angle and the output is a value from negative 1 to 1. So if we take the inverse of that, the input is now a value from negative 1 to 1, and the output is now an angle, except this time it can't be any angle. It has to be an angle between negative pi halves and positive pi halves. So let's take a look at a few examples of problems that require the inverse sine and specifically relate them to the restrictions on the domain and range. For our first question, let's take a look at a value we're familiar with from our unit circle. Find or evaluate inverse sine of 1/2. So 1/2 is a value on the unit circle, and the sine, if you're thinking about the unit circle, so let's take a look at quadrant 1. The sine is the second value of the ordered pair. So if you're looking at your unit circle, these are the 3 values, as well as 1, 0, and 0, 1. So we're looking for the angle for which sine is 1/2. Which angle in quadrant 1 is the sine 1/2? The answer is pi 6. And that's how you evaluate an inverse trig function. Now double check your domain and range. Is x a value between negative 1 and 1? Is y, the output, a value from negative pi halves to positive pi halves? That's how we know we've calculated the inverse correctly. Let's try that again, but this time using the other notation. Remember that inverse sine and arc sine mean the same thing using different notation. This time, let's calculate it using a negative value. So with sine, we want to be careful. Answers in the second quadrant and answers in the third quadrant aren't going to work because we had to restrict the domain of sine in order to invert it. So think of negative pi halves to positive pi halves as just quadrants 1 and 4. This down here is negative pi halves. All the way up here is pi halves. We want all of our answers to be from negative pi halves to positive pi halves. With that in mind, we're going to find negative rad 2 over 2 down here in the fourth quadrant. And the angle we're going to find it at is not 7 pi over 4, but is actually negative pi fourths. We need our answer to be within our acceptable range. Let's take a look at the domain and range restrictions for inverse cosine as well as inverse tangent and do a sample problem of each. So in order to find or define inverse cosine or arc cosine, we need to take a look at the original cosine curve. Just like sine, cosine is not considered invertible because it has a repeating range. However, just like sine, we can restrict the domain of cosine to find an inverse. Unlike sine, we don't need to go into the negatives to make sure that our range doesn't repeat. So cosine starts at 1. And as you can see, these are all of the positive values and these are all of the negative values. So the restriction on cosine is 0 to pi, because from 0 to pi in a continuous curve, cosine does not repeat its values. That means for the inverse function, remember this is domain of cosine, which makes it range of inverse cosine. The range of answers, or the acceptable angles, are all going to be from 0 to pi. Well, the domain of the inverse is going to be the same as the range of cosine. The range of cosine is negative 1 to 1. I can evaluate inverse cosine so long as my input values are from negative 1 to 1 and my output values are from 0 to pi. Let's take a look at two cosine examples. For our first example, we'll do arc cosine of 1. And for our second example, we'll do inverse cosine of negative 0.4. Oops. For the first example, we're looking for the angle on the unit circle between 0 and pi whose cosine value is 1. That angle is 0. Since negative 0.4 is not on our unit circle, we're actually going to use our calculator in order to compute the inverse cosine. With your calculator, type second cosine of negative 0.4. The answer is about 1.98 radians. If you are in degree mode, the answer is about 114 degrees. Let's repeat the same process for tangent. Y equals inverse tangent of x. Y equals arctan of x. In order to find the inverse, we need to make sure that we restrict the domain. Let's take a look at the graph of tangent and find what domain tangent is invertible on. Unlike sine and cosine, tangent repeats its values or has a period of pi. So if we're graphing tangent, we know that it originates at 0 and has an asymptote at pi halves, and that it crosses the axis again at pi. Same thing on the other side. It has an asymptote at negative pi halves, and it crosses the axis at negative pi. So how can we restrict this domain in a way that tangent isn't going to repeat any y values? This is what's going to make tangent invertible. Well, you can see this nice continuous curve right here goes through all the range of tangent without repeating any values, except for the undefined values at the asymptotes. So the domain of tangent that makes it invertible is negative pi halves to pi halves, which means that the range of inverse tangent is negative pi halves to pi halves. Now notice, unlike in the last two examples, I did not use inclusive inequalities because we can't include the asymptotes since those values technically repeat. Also, unlike sine and cosine, tangent does not have an amplitude. That means its range goes from negative infinity all the way to positive infinity. Since the inverse tangent has a domain equal to tangent's range, that means our domain is all real numbers. Let's take a look at two inverse tangent examples. For the first example, let's find the arctan of rad 3. And for the second example, let's find the inverse tan of 3. Is rad 3 a tangent value from the unit circle? Yes. Which angle on the unit circle between negative pi halves and positive pi halves has a tangent value of rad 3? The answer is 60 degrees or pi thirds. 3 is not a tangent value on the unit circle. So for inverse tangent of 3, we're going to use our calculator and give an approximate value. The approximate value for inverse tangent of 3 is 71.565 degrees. These are the basic inverse trig functions and their restrictions that we're going to be using to solve equations involving trig functions. This is the end of part 1 of the video notes for Objective 7.